Hey, welcome back to Fat Mama Physics. This is a video on the work-energy theorem, and we are going to answer the question we got from our last video in how do we get the work done by the net force being exactly the same as the change in kinetic energy. We are going to use this video to figure out why and how that is possible. So we're gonna do a few things in terms of equations and putting things in, and it's the art of deriving equations, which we will be doing in this video. So no examples. So let's get to it. Okay, we're gonna play around with a work equation. First of all, we know that work is the force times the displacement in that direction, and if not, cosine theta, theta being the angle between the force and the displacement vector. F net we know is mass times acceleration, Newton's second law. Now for the work done by a net force, that's being more specific, in which the force is going to be the net forces, the sum of all forces acting on your object, times your displacement. But when we find the net force on our object, usually that is in the same direction as an object's acceleration, and for most of the time, your object is going to be gaining displacement, or it's going to be displaced in that same direction of acceleration. That just means F net will be in the same direction as displacement, so that the angle between them will be zero for the most part. There might be some exceptions which we are not going to go into. But then, when you do have an angle of 0, cosine theta just becomes 1, and it leaves this equation. 1 times anything is just that thing itself anyways. So, now we have some building blocks. Let's see what we can do. First things first, we have F net. Let's just put F net and substitute that into our work equation, which is just MA. So we're going to put MA as F net in the work equation. See what that gives us. And that just gives us mass. Lots of mass, yo. Okay, sorry. We know that as an object accelerates, it will increase its speed to some final speed relative to the initial and be displaced a certain amount according to this kinematics equation. Didn't we use that in the previous video before? So let's do something in which we will rearrange this equation to get acceleration times displacement is equal to blah 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 something. Because why? We can then substitute that over here in mass. Let's do some algebra to isolate for AS. So solving for AS, we need to subtract the initial velocity on both sides of the equation, and then dividing both sides by 2, which then leaves us with just AS. Okay, now we can substitute the AS into the mass. We get M times the AS, the mass times the AS, so M times the AS, which in here is V squared minus U squared, all of it divided by 2, to get this one over here. So we no longer have acceleration, we no longer have displacement or AS. We are only left with final and initial velocities. It's starting to look suspicious now. Let me make it a little bit more obvious for us to see what's going on. I'm going to move the 2 divided by 2 outside, which is going to give us mass divided by 2, and in brackets, final velocity squared minus initial velocity squared. Still not obvious enough? Well, let's keep going. Well, we can put the one, if it's m divided by 2, that's the same as 1/2 times m, mass, and in brackets, v squared minus u squared. Still not obvious enough? Well, let's keep going. Let's distribute 1/2 m into each of these speeds. So we get v squared minus 1/2 m u squared. Ooh, what do we have here? Where have we seen 1/2 mv or 1/2 m any speed squared? Isn't that kinetic energy? And if we have 1/2 mv final velocity squared, wouldn't that just be the final kinetic energy? And then this is u, which is initial velocity. That just means initial kinetic energy? And then if we take the difference between the final and the initial, isn't that just the change in kinetic energy? Oh my god! So all of that came from the work done by the net force. Sometimes we just call it the work done on the object because it assumes it sums up all the forces acting on the object anyways. So here, we've just shown that the work done on the object is equivalent to the object's change in kinetic energy. So that's the work done by a net force causes the change in the kinetic energy. Let's write that down here. This is what we found. Wow, so that's interesting. Is it a be-all, end-all equation? Not necessarily. You still need to know what is happening in your equation. For example, there are not all the time F net and displacement are going to be in the same direction, so that's something you need to be aware of. Other than that, it does work for a good number of systems in which they accelerate in a certain direction. And this is why, in our previous video, how when you calculate the change in kinetic energy was exactly the same as the work done by the net force acting on that snowball. We just derived that relationship right here. So, thank you for watching this video. Hopefully, that gave you some insight. In the next video, we are going to apply the work-energy theorem to actual examples and questions. So, stay tuned. Thank you for watching. Fat Mama Physics signing out.